What does the GeForce 2 Ultra, the GeForce 3 Ti 500, the GeForce 4 Ti 4600, and the GeForce FX 5900 Ultra all have in common? Well, they all have 4 dual texturing pixel pipelines. So what did NVIDIA do to make each generation so much more powerful? Well, that's what I'm looking to find out. NVIDIA introduced the world to the first 4-pipeline GPU with the GeForce 256 in 1999, doubling the standard 2-pipeline architectures that pretty much all design houses used up to that point. However, older architectures were capable of multi-texturing in a single pass through each of those pipelines, something the GeForce 256 lost. To rectify that, NVIDIA released the refreshed GeForce 2 series just 6 months later, which added to the 4-pixel pipe architecture a second texturing unit in each, allowing games which use lots of texturing effects much less of a performance hit. This 4x2 setup, as it turns out, would be NVIDIA's design of choice for the next 3 years, across 4 generations. And yet, the performance difference between them is enormous, much more than the gentle increase in clock speed can be attributed. In order to really find out how much NVIDIA improved the performance of their architectures over this 4-year span, we need to take 4 flagship graphics cards from each generation and clock them all the same. I chose the earliest graphics card as a baseline, so none of the cards will have a problem running it. All cards are running at 250 MHz core and 460 MHz effective for the memory. In most cases, the biggest rise comes from the GeForce 3 over the GeForce 2. The performance after the GeForce 3 rises more incrementally in general. In the case of Doom 3, performance between the GeForce 3 and GeForce 4 are identical. However, in Unreal Tournament 2004, the 4600 sees a huge leap over the Ti 500, likely owing to the fact that the game likes having more than 64 megs of video memory. In almost all cases, the FX 5900 Ultra shows a nice improvement, with the exception being Half-Life 2 and DirectX 7 mode, which quickly hits a CPU wall. Where you see the gray bars on this graph, each graphics card is running at its respective maximum DirectX mode. So in the case of the GeForce 3 and GeForce 4, that would be DirectX 8. And in the case of the GeForce FX 5900 Ultra, DirectX 9. All cards are from a similar lineage. They're all NVIDIA-made 4x2 architectures that, in this case, are all clocked the same. So where are the improvements in performance coming from? One thing that I can't even out is vertex processing. The GeForce 3 architecture more than doubles the geometry throughput of the GeForce 2 when efficiency improvements are accounted for. The Ti 4600 just about doubles that, and then the FX series shows a massive improvement in high polygon tests in 3D Mark 2001, suggesting 3 times or more performance jump there. And then you have other efficiency gains, particularly in regard to memory bandwidth use. Whereas the GeForce 2 spent its bandwidth relatively wastefully, the GeForce 3 began the concept of the crossbar memory controller, splitting up the 128-bit interface into 4 parts so not every request required the entire bus. The GeForce 3 also implemented features equivalent to ATI's Hyper-Z technology from a generation earlier, which prevented unseen polygons from being rendered and reducing the bandwidth consumption of the Z buffer. The FX 5900 Ultra takes these improvements further while coupling it with a 256-bit memory interface. So even though I clocked the memory the same as the other cards, bandwidth is still doubled. So what does this all mean? Well, obviously there's a lot more to the graphics processor than pixel pipes, but I'm sure most of you watching this already knew that. What's maybe more interesting is the extent to which performance can be improved within the same basic GPU configuration. In an era dominated by pixel and texture fill rates, before there was ever any mention of gigaflops and concurrent processing, the graphics card was a relatively simple device, where pipelines and texture units were just about the only fixation among enthusiasts. Yet even under those restrictive terms, there were still ways to enhance performance, edging them ever closer to those seemingly elusive theoretical numbers, a task still at the forefront of GPU engineering today. I hope you found this little exploration interesting, and you can check back for more dissections of graphics processing units in the coming weeks. Thanks for watching. I'm Nathan, and this has been Pixel Pipes.